In this lesson, we're going to look at general graphs of exponential and logarithmic functions. So we're going to start off with graphing exponential functions, and we'll start off with making a table of values for y is equal to 2 to the x. So 2 is the base, and x is the exponent. And if I look at this, let me put in, let's start with -1, and then 0, 1, 2, and 3. So when x is -1, that means it's 2 to the negative first, which that means it's 1/2. And then at 0, y is 1. And then we have 2, and then 2 squared is 4, and 2 cubed is 8. So there's my table of values, and we are going to just sketch a rough graph using these coordinate points. So if I look here, I don't have, all my y values are positive. So when I come over here and kind of sketch out an x-axis and a y-axis, I'm going to be biased towards the positive y. So there's my y, and if you have graph paper, by all means, do this on graph paper. I'm just making a rough sketch just to kind of get a general idea, so that's what I'm doing here. Alright, so I'm going to plot these points. -1 is at 1/2, which is going to be hard for me to do right here, but -1 is about 1/2, so it's roughly there. At 0, I'm at 1, and then at 1, 2, if I move to the right one, I go up 2, and then 2, 4, and then finally 1, 2, 3, 4, 5, 6. I need 2 more points on here to graph 3, 8. You can graph this on your calculator, you can graph this using Desmos on your Chromebook, whatever. You should see the same general curve. It moves up and increases. So these curves have some basic properties to them, whether it's 2 to the x, 3 to the x, 4 to the x, e to the x, they all have some same general properties. As you look at this, and you can write this stuff down as I say it, the y values are approaching 0 as x approaches negative infinity. So again, as I move out in the x direction, my y values are decreasing. Why will they never be negative, though? They decrease asymptotically until they approach 0. But I'm not sure. Now think to yourself, why would they never cross that x-axis? And we can talk about that as we come back to class. So as x approaches negative infinity, my y values are approaching 0, but they never get there. That's actually a horizontal asymptote at y is equal to 0. So we call that a horizontal asymptote. Every exponential function has a horizontal asymptote. And then the other property of an exponential function is they cross the y-axis at 0, 1. When I don't have any translations going on here or dilations, they cross at 0, 1. So we'll write down a couple things here to denote some of these properties. So here we have a sketch of a generic exponential function. I'm going to call this y is equal to b to the x. So we can kind of look at these properties. Exponential functions, they always cross the y-axis at 0, 1, because b to the 0 is going to bring back a 1. And we have a horizontal asymptote because as x approaches negative infinity, y approaches 0. So my horizontal asymptote, I keep making my y's like x's, my horizontal asymptote is y is equal to 0. And given my function y is equal to b to the x, where b is the base, x is the exponent, then this point is always on the graph, 1, b. If I move to the right 1, I go up the amount of the base, because b to the first is going to be b. That's always on the graph. Finally, my domain is going to be all reals. I can replace x with any value I want and it will yield an answer. My range, however, my range is going to be greater than 0 because I have that horizontal asymptote, and I cannot create a negative value no matter what value I substitute in for x. So we're going to now look at logarithmic functions. And logarithmic functions are the inverses of the exponential functions with the same base. And we know from previous experience that if I graph a function, its inverse is going to be the reflection over the line y equals x. So while exponential functions will curve up, log functions will curve to the right. So and everything reverses between the two. Instead of a horizontal asymptote, we're going to have a vertical asymptote. So let's choose some points here to put in. Now we have to be careful because now our argument for a log function is has some restrictions. If I want to graph y is equal to log to the base 2 of x, I've got to be careful with my x values because my argument cannot be negative and it cannot be 0. So when I think about this, I'm graphing the inverse of, or if I wrote this in exponential form, that's really 2 to the y, and those are my x values. So if y is 0, x is going to be 2. If y is, let's say y is negative 1, I know I'm a little out of order, x is going to be 1/2. So if y is 1, 2, and 3, x is going to be, I got to fix this guy up here. Let me do this again. When y is 0, x is 1. When y is negative 1, x is 1/2. And then when y is 1, x is 2, and then 4, and then 8. That's better. So if I graph those, now I cross the x-axis when y is 0. And I have 1/2 and negative 1. So he's curving down here. I gotta put him right in the spot right there. And then at 2 I go up 1. At 4 I go up 2. And then at 8, 1, 2, 3, 4, 5, 6, 7, 8, I go up 3. So he is the reflection of the exponent, the equivalent exponential function over the line y equals x. So the properties also reverse. We now have, instead of a horizontal asymptote, we now have a vertical asymptote. Again, that's because my argument cannot be 0 or negative. So we have a vertical asymptote. It's a v. We have that. And that is at x equals 0. My range this time is all reals. And my domain is going to be x is greater than 0. And then for the parent function, 1, 0 is on the graph. And if I have a base of b, if I have y is equal to log to the base b of x, then b1 is on the graph. So it's the reflection of the equivalent exponential function. So given those two parent functions, we're going to work to graph others in class and also take a look at how we do this with our calculator to help us out. Some calculators we have to use change of base, some calculators we don't. So we are going to work more on this in class.